Hi everyone, my name is Peter Felfer, and in this video I'm going to show you how to calculate a proximity histogram or proxygram from your atom probe data. And what you need to do that is actually you need some atom probe data, obviously, .pos files and maybe some subfiles of that. And you need to have an interface like this one here. I have to find it in Blender. There's also some other algorithms that you can use like either concentration surfaces, isosurfaces, and you can calculate those in Matlab. But you can do, for example, some manual modeling in Blender, or some manual modeling, some sort of semi-automated modeling using my algorithms, and you get one of those grain boundaries, and we'll calculate a proximity histogram from that. In order to get your data into Matlab, you need to obviously have that in some sort of file format, and choose wavefront OBJ because it's the most common one. So if you don't already have it, you'll go export wavefront OBJ, choose Y forward and set up. That's great. And sometimes if there's multiple objects, just select go selection only. We don't need modifiers and so on and so forth. So just obj is objects and selection only, but I've got that one already, so I don't need to export it. And off we go into Matlab. So once you've got Matlab open, it actually is a fairly easy thing to do. There's a variety of ways. You can not pass any information to the algorithm, then it will just come and prompt you to provide some information. So this is the approximate IE value package of algorithms that come with a tutorial. You can download it from a web page, and we'll just go quick proxygram. And if you don't type anything else, it will come up with the system default dialogues, and you can go and choose your .pos file, which is the file of all atomic species. Then the obj file, which is the interface. And then you can go and either select a different POS file that you want to calculate the proximity histogram for. So say you're having a .rng file and you want to create a proxygram for a certain species, or you've come up with another way of creating a POS file. Say you want to see only the clustered atoms. Then you can load in another .pos file and load it in. Or you can go select species and use an XRange file, which is my file format. You can download an editor. It's XML based. You can download an editor from a web page. It's very easy to deal with. So that's in there as well. And you can choose if we want to map it by atomic species, isotopic, or ionic. I'll just go atomic. And I want to have all three, so I want to see how many unranged silicon. It's artificial data, so there's nothing unranged. So we'll just go for the two main ones in there. The bin width, I'm just going to choose 0.5 nanometers, so I know what the statistics are going to stand for it. If it gets a little bit noisy, obviously make your bins a little bit wider. If you have a question of what the optimum bin width is, I can exactly tell you there is no such a thing. It's always a trade-off between the how fine your steps are and how much you're washing out. So you can see you've got the carbon and silicon. You can move the legend around, and let's just zoom in, constraint, zoom vertical, and there we go. This is our proxygram. We can go and do that for multiple species. Easy enough. So first part. Second part is doing it by hand. So you might want to use just the Matlab command line, like I do it quite a lot of times. In which case you load in your POS file with the read POS command. So grain boundary. Then you load in your obj file with the read wavefront obj command. which is actually a struct that you get, so you don't directly get the object we're going to be working with, and it's got vertices, which is if you go into here, if you go into here and look at the interface, then oh, wrong one. These are the vertices, and these are the faces. So the vertices are points with x, y, z coordinates, and the faces are just since we're only using triangles, are just three just three numbers for each face, which just say which vertices the face connects. Another thing, before you export your wavefront OBJ, you need to make sure that you've got only triangles and no quadrilaterals. You can assure that by going Control T, so marking everything and going Control T. Since it's all triangles already, it doesn't really matter. Anyway, so we'll produce a Matlab patch from that. So we go fv.vertices are the OBJ vertices, fv.faces are the vertices of the first object in here. We're only going to have one object, but you could have more than one. So you can see here, type faces and vertices, and this is the list I was talking about. And that's pretty much what we need. So we could use another species now, or an X-range file. But since if you have the X-range file, you would probably use a GUI variant anyway. We'll just use another species. So we'll go in the pos file. So I'll just to show you the pos file is X, Y, Z coordinates, and the master charge column. I've just given everything that's solvent atom, come on, load a bit faster. Everything that's solvent atom, I've given a master charge of 1, and everything that's a solute atom, I've given a master charge of 2. So we can go solute. Solute is where the fourth column of the pos is larger than 1.5 and 104. And there we go. And now in order to calculate the proxygram, we'll just go quick proxygram of the pos file, the interface called fv, the species called, I'll call it solute, and bin width 0.5. So we should get the same result as before, just without the solvent. And there we go. The only difference is you can see, of course, when you pass the pos file, it doesn't know what you're passing. So the legend says external, but you can go and edit that later and call it, I don't know, I'll call it carbon, I think. Up. And that's it. We've got the proximity histogram. Next tutorial is about how to calculate an interfacial axis value from that.